Welcome back. So, let us continue with the example that we are discussing that I had initiated towards the end of the last lecture. Let me read out the example once again very quickly. It goes as follows. A fixed income analyst wishes to forecast the expected return of a bond portfolio for the next year. He gathers the following information and assumes that no reinvestment of coupons cash flow takes place. The average coupon rate of the portfolio is 3% per annum. The coupon frequency is semi-annual. The horizon analysis, that is the holding period, projected holding period, that is 1 year, and the average bond price of portfolio at t equal to 0, that is right now, is 101.500. The average life of the bonds constituting the portfolio is 7 years. The YTM corresponding to a price of 101.500, that is the current price, the t equal to 0 price, is 2.76% per annum. We assume that the initial yield curve is upward sloping and the 6-year yield is at 2.56%. Please note the 7-year yield, that is the t equal to 0 yield corresponding to the price of 101.500 is 2.76%. At the end of 1 year, the bond will have a remaining life of 6 years, and it is projected that at that point in time the YTM for a 6-year bond will be at 2.56%. It is also given that at the YTM of 2.56%, that is at the end of 1 year, the price of the portfolio will be equal to 102.419. So, let me repeat this. This is the cardinal content of this question, this problem. T equal to 0, YTM is 2.76% and the price is 101.500 and the life is 7 years of the bond portfolio, and at t equal to 1, the remaining life, that is of the bond portfolio, will be 6 years, and because the yield curve is upward sloping, the YTM has changed from 2.76% to 2.56%, and evaluated at 2.56 YTM, the 6-year bond carries a price of 102.419. This is given in the problem. The analyst also projects that a general decline in interest rates of 50 basis points is likely. A decline in credit spreads is expected as well. Combining the credit spread decline for the portion of the portfolio in credit risky bonds with the general 50 basis points decline, the analyst projects a 54 basis points. So, by apportioning or by distributing the decline in the credit spreads over the credit risky bonds, you see the entire portfolio may not comprise of credit risky bonds, it may comprise of some credit risky bonds and some government bonds as well, for example. And the basic thing is, if you distribute the impact of the credit spread over the entire portfolio, do some kind of an averaging over the entire portfolio of the change in credit spread, it turns out to be approximately 4 basis points assessed or apportioned over the entire portfolio. Added to this is the 50 basis point general decline. So, we end up with a total decline of 54 basis points in the across the portfolio. The expected yield and spread change of portfolio is therefore minus 0.54%, as I explained just now, 54 basis points. The modified duration is given as 5.60 and the modified convexity of the portfolio is given as 28. To assess credit losses, the analyst estimates 0.071% of the portfolio's bond value will default and 50% of any defaulting value will be recovered, 85% will not be recovered. So, on the average, if a particular bond defaults, then 15% will be recovered, 85% will be the default amount, it will not be recovered. Then as far as the currency impact is concerned, the portfolio has invested 40% in foreign denominated bonds and the investor expects the foreign currencies to appreciate by 3.925%. Now, we start with the income or the current yield. This is quite straightforward. This is elementary. The annual coupon payments. What is the annual coupon payment? The annual coupon payment is 3.00 over the current market price, which is 101.50. So, that gives us annual coupon yield of 2.956%. So, this is straightforward. You divide the annual coupon payment by the current market price, you get the income yield or the current yield, and that turns out to be 2.956%. Now, as far as the annual coupon yield, this is the per annum yield. Please note this 2.956%. If you want to convert it to a periodic return, you can, for example, the half yearly return or the return over a 6-month period will be equal to 2.956 divided by 2, that is equal to 1.478%. Please note, we have not considered reinvestment of coupons in solving this problem. We have assumed that the cash flow or the coupon payment at t equal to 6 months will not be reinvested. If we assume that the reinvestment does take place, and for example, if we assume a reinvestment rate of 2% per annum, then the cash flow of 1.5 that will take place at t equal to 6 months will be reinvested for the next 6 months, and we will get at the 2% per annum or 1% for the 6-month rate or the half year rate. So, we will get 1.5 into 1%, that is 0.015% of the return as reinvestment income, if we assume a reinvestment rate of 2% per annum and apply 1% over the amount of coupon payment that occurs at t equal to 6 months, which will be reinvested from t equal to 6 months to t equal to 12 months or 1 year, that is a 6-month period. The roll down yield relates to a bond pricing model, assuming that the yield curve is unchanged. So, assuming that the yield curve is unchanged, what will happen? The bond is priced today at t equal to 0 as a 7-year bond at a YTM, which corresponds to a 7-year interest rate and which is given as 2.76%, at which the value of the bond has been estimated or has been arrived at as 101.50 units of money. At the end of 1 year, the bond will have a remaining tenure of 6 years, and assuming that the yield curve, spot yield curve does not change, you shall use the YTM rates corresponding to a 6-year maturity, which is given in the problem as 2.56%, and at this rate of YTM of 2.56%, the value of the bond increases to 102.419. So, 102.419 is the projected price at t equal to 1 year, assuming that the yield curve is unchanged and the bond is now a 6-year bond. It started as a 7-year bond at t equal to 0. Now, it is at t equal to 1, and therefore, the 6 years remain to maturity, and therefore, the 6-year spot rate becomes relevant for the YTM of this bond, which is given as 2.56%, and using this 2.56%, we arrive at the price at t equal to 1 year of 102.419. The roll down yield will be given by the projected price at t equal to 1 year at the end of the holding period or at the end of the investment horizon, which is 1 year in our problem, and that is 102.419 minus the initial price, which is 101.50 divided by the initial price, that is 101.50. So, that turns out to be 0.905%. The rolling yield is the aggregate of the income yield or the current yield and the roll down yield. The aggregate is sometimes called the rolling yield, and that turns out to be 3.86%. Now, as I mentioned just now, if you have a flat yield curve, then and you have a bond quoting at a premium, then the premium gets amortized over the life of the bond until its maturity in a regular or in a continuous manner, and as a result of it, the price of the bond at t equal to 0 would be higher than the price of the bond at t equal to 1 year, will be higher than the price of the bond at t equal to 2 years, and at the end, at the maturity, the bond will reach its par value. This is dictated by the considerations of arbitrage free pricing, In the case of the of a bond quoting at discount, the discount is amortized just like the premium is amortized in the previous case, and the amount of discount gradually diminishes with the remaining maturity of the bond. However, this is not necessarily so when we have a sloping yield curve. For example, as I mentioned, in the case of the upward sloping yield curve, what will happen is that the t equal to 0 price will be based on a longer spectrum of interest rates t S01, S02, S03, S04 up to S0 capital T, where capital T is the maturity. Whereas, say if the investment horizon is h years, then the price of the bond worked out, or the projected price of the bond worked out at h years will be based on the remaining spot rates, that is starting from t equal to h, the rate for a 1 year deposit, that is S01, S02, S03, S04 up to S0 t minus h. Now, let me repeat, for the pricing of the bond at t equal to 0, you have spot rates varying from S01, S02, S02 up to S0 t, capital T. Now, when h years have passed, where h is the holding period, the remaining life of the bond is t minus h years. Therefore, when you assuming that the yield curve does not change, the relevant rates will be S01, S02, S03 up to S0 t minus h. Now, because we are considering here an upward sloping yield curve, the price or the YTM arrived at on the basis of the first price, that is the t equal to 0 price, will be higher, because it includes rates from t equal to h minus t to t equal to capital T, which are higher compared to the rates H01, H02, H03, because we have an upward sloping yield curve, whereas the price at t equal to h would comprise of the rates H01, H02 up to S0 t minus h, and that will be lower, and thus the YTM would be lower and the price would be higher. So, let me read out what I have explained just now. With a sloped yield curve, this may not always be true. This is because the bond price PH means price at the end of the holding period, price at the end of the investment horizon, will be worked out at a lesser term to maturity t equal to h to t equal to capital T, that is the period is t minus h, and then its price at t equal to 0, which is calculated with a term to maturity of t equal to capital T. If the curve is upward sloping, the shorter end rates are lower, thus the rate for maturity of t minus h are lower than the rates for maturity of t equal to capital T. Hence, the price calculated at exit at t equal to h will be at a lower rate and hence higher. Now, expected price change, as we have discussed, the analyst has projected a decline in interest rates of 0.54%, a decline of 0.54% in interest rates. The duration and convexity are given as 5.60 and 28, and we can simply apply the duration convexity model, which is embedded in this particular equation. Let us call it equation number 1, and using equation number 1, where MD is the modified duration plus 1 by 2 into effective convexity into delta y square, that is on computation turns out to be 3.065%. So, this is a price change, this is the positive price change due to the decline in interest rates. The analyst, as far as the credit losses are concerned, the analyst estimates that 0.071% of the portfolio's bond value will default and 15% of any defaulting value will be recovered, which means 85% of defaulting bond value will be lost, and this implies that the expected credit losses are 0.071% into 0.85, that is equal to 0.06%. This is straightforward. Similarly, the expected gains or losses versus the investor currency, the 40% of the investment in the bonds is in foreign denominated bonds, and the expected increase is 3.925%, and therefore, the effective increase measured over the entire value of this portfolio is 3.925% into 0.40, that is 1.570%. So, here is the summary of the return components. The yield income or the annual coupon over the current bond price is given as 2.956%. The roll down yield, we have worked it out as 0.905%, and the price change due to investor yield change predictions is 3.065%, and as far as credit losses are concerned, it is minus 0.06%, and as far as the currency gains are concerned, that is 1.57%. The aggregate expected total return for the year is 8.395%. When you algebraically add all these quantities, taking care of the minus signs wherever relevant, you end up with a value of 8.395%. Okay, so this is the example, this is the illustration of what could be the possible return components when you make an investment in a bond portfolio. Let us now talk about a new topic. Suppose you are given you have a liability that is going to materialize at the end of 5 years, and that is represented by a bond. Let us say it is a 5-year zero coupon bond, that is a liability for you, that maybe you have to redeem, let us say, and we need to immunize ourselves against any changes in interest rates in the intervening period between t equal to 0 and t equal to 5 years, when the liability is to be redeemed. Now, for this before we get into the nitty gritty of this particular problem, which is a very fundamental problem in the context of fixed income portfolio management, let us recall some features of the duration convexity model, specifically and in general bond analysis that I have discussed in the previous lectures. The duration convexity model is given by the equation, that is equation number 1 here, right at the top of your slide. In terms of the Macaulay's duration and convexity, we have the left hand expression, that is this expression, and in terms of modified duration and modified convexity, which is usually used in the CFA examinations, we have the second part of the equation, which I have represented by the arrow. Now, the duration model works well on the YTM, and that is, it assumes a single rate for all maturities. The duration model works on the YTM, that is, it assumes a single rate for all maturities. Why? That is, it ignores the term structure of interest rates, it assumes a flat spot rate curve. I have already explained this point a number of times. There are two fundamental assumptions in duration. Number one, that the term structure is flat, that is, all the cash flows are discounted at the YTM rate, that is number one, all cash flows from the bond are discounted at the YTM rate, and number two, the shift corresponding to an interest rate change is a parallel shift in the yield curve, that is there is no asymmetry insofar as the shift in the yield curve is concerned. The dy that we consider in the duration model, the dy that you see here, the dy that you see here or here is uniform across all maturities. In other words, the term structure or the spot yield curve shifts parallel to itself by an amount of dy. So, that is the second fundamental assumption. Two important assumptions in the duration convexity model. Number one, we work on the basis of YTM, that is, we assume a flat yield curve, and then the shift is also flat, that is, the shift is parallel to the spot yield curve in the original place. It assumes a straight line yield price curve in the locality of the given yield. If you use the only duration, that is, if you use only this term, then what you are not considering the convexity or the curvature of the yield price curve, that is how the behavior of the price corresponding to different yields, that is captured by the yield price curve. Please note the difference between yield price curve and the spot yield curve. The yield price curve is the relationship between price and changes in yield, or changes in yield along the x axis and price along the y axis, whereas the spot yield curve gives you the YTMs corresponding to different maturities along the x axis and the corresponding YTMs along the y axis. So, they are fundamentally different objects. Now, it assumes a straight line yield price curve in the locality of the given yield. This is because we arrived at the definition of duration using the concept of Newtonian differentiation, and in the Newtonian differentiation framework, we assume that in the infinitesimal neighborhood, infinitesimal proximity of the point at which we are working out the derivative, the curve or the functional relationship y equal to f x is assumed to be a straight line within that very narrow point, narrow proximity both to the left and right of the point under reference. So, convexity accounts for the curvature of the yield price curve, not the spot yield curve. So, convexity basically has nothing to do with the spot yield curve, nothing to do with the term structure of interest rates. It accounts for the curvature that is embedded or that is there in the yield price curve. The term structure is unattended. It is not captured in the Macaulay duration or modified duration framework. As I mentioned, we assume a flat term structure, we assume a constant value of y, which is the YTM, and if you assume a constant value of y, obviously you are ignoring the functional relationship between the spot between the maturities and the corresponding spot rates. Now, one very important point that we have here is the convexity correction is always positive. If you look at this equation, let me call it equation number 1 on this slide. This is dy squared. Therefore, irrespective of whether dy is positive or negative, this correction, so long as the convexity is positive, and in fact straight bonds always have a positive convexity. So long as the convexity of the underlying portfolio is positive, so long as this is greater than 0, this will always be greater than 0, and therefore, the convexity correction into the price change or the correction due to the curvature will always be positive. So, this is very important. The convexity correction is always positive, so long as the convexity of the bond is positive, irrespective of the direction of change of rates, that is irrespective of the sign of dy, irrespective of whether rates are going up, dy is positive, or the rates are going down, dy is negative, the convexity correction is always positive. The ramifications of this particular attribute shall become apparent as we move along today's lecture. Convexity of straight bonds is invariably positive. Convexity of callable bonds may be negative at points where the option is at or near the money. You see, this is the reason behind this, as I explained in the earlier lectures also, is because as the bond approaches, as the price of the bond approaches the exercise price, when the interest rates become so low that the price of the bond approaches the exercise price, the change in the price corresponding to a further change in interest rates is going to be less, and a point in time will come when changes in interest rates will not be accompanied by any change in price. Why? Because as soon as the price goes above the exercise price, the issuer will exercise the call option and call back the bond. So, in no way can the investor sell the bond in the market at a price higher than the exercise price. So, what will happen? As the market interest rates decline, the price goes up, price keeps on going up until the point in time that the call option becomes in the money or near the money, until when the exercise price is reached, and once the exercise price is reached, any further decrease in interest rates will not result in a further increase in price, because the investor will because the issuer will exercise the option. So, if liability duration and asset duration is matched, this is a first order matching. If the liability duration, please note this point, duration and asset duration is matched, this is a first order matching and will operate reasonably well for small parallel shifts of the yield curve. Let me repeat, this is another important point. If liability duration and asset duration is matched, that is the net duration is 0, this is a first order matching, duration is the first order approximation. So, this is a first order matching and will operate reasonably well for small parallel shifts of the yield curve. However, larger the convexity of the assets or liability, greater will be the second order correction term. Naturally, larger is the convexity, greater is the magnitude of the second order correction. And please note this point, this convexity correction is always positive. So, if what happens if the assets convexity is higher, if the liabilities convexity is lower, irrespective of the direction of movement of the interest rates, the correction due to convexity of the assets would be higher and the correction due to the convexity of the liabilities will be lower. Please note both of them will be positive, and as a result of which at least at first sight the benefit will accrue to the investor or to the party who is doing the portfolio management exercise. The second order correction term is positive always for straight bond. As I mentioned, straight bonds have a positive convexity, and dy square is always positive irrespective of the sign of dy. Therefore, whether the interest rates increase or the interest rates decline, dy square will always be positive. If c is positive, the convexity term in totality is positive, and therefore and furthermore if the asset side convexity is higher, naturally the positive increase in price or the increase in price due to the convexity correction will be more for the asset side compared to the liability side. Hence, higher the convexity of assets over liabilities, greater will be the positive correction in asset price over liability price, that is, the asset price will move more favorably than the liabilities price. This is what I explained just now. However, greater convexity, as I mentioned, there is nothing called free lunch in this world. Greater convexity means higher prices, higher corrections in prices, and if the asset side has more convexity, the insulator or the immunizer has the opportunity to gain, but the important catch is given in this paragraph. The catch is greater convexity also implies greater dispersion or variability of the cash flows corresponding to interest rate changes. This I explained with an example, a detailed example when I talked about the concept of duration. Now, we talk about immunization. Again, this is more of a revision stuff. I have talked about immunization in an earlier lecture. So, let us quickly run through it. Immunization is a fixed income management process in which the portfolio is managed to minimize the variability. Here lies the objective of immunization. It is not to maximize the return, it is to minimize the variability. Please note this point. When you are talking about immunization, you are talking about protection. You are talking about the protection against what? Against interest rate risk, changes in interest rates. When you are talking about immunizing a portfolio, what you are interested in is minimizing the variability, the change in the price of that portfolio if the interest rates show changes or show deviations from projections. So, immunization is a fixed income management process in which the portfolio is managed to minimize the variability of the rate of return earned over a specified time period. That means, now if a portfolio is immunized, the impact of interest rates on the portfolio is minimized, it is eliminated or at least minimized, and that means what? That means the future value of the portfolio can be confidently predicted. Interest rates are a random variable, interest rates are stochastic. So, interest rates change. If interest rates change, but your portfolio is so constructed that the impact of interest rates is eliminated, is minimized, then you can confidently predict the future value of the portfolio, and therefore, you can work out if enough funds are invested initially, then a known future liability can be funded. The goal of the immunized portfolio is to earn the initial portfolio IRR. This is important. The significance of this term will be clear as we progress along today's lecture, but you see the objective is that if you are immunized, if you are protected, if you are cut off from the rest of the world, the portfolio is cut off from the rest of the world, what will the portfolio earn? The portfolio will earn its initial portfolio IRR, that the cash flows that are going to be generated from the portfolio will not change due to changes in the environment represented by changes in interest rates, and as a result of which the initially projected or initially estimated interest rates will be earned, notwithstanding the fact that the market interest rates change. So, the goal of the immunized portfolio is to earn the initial portfolio IRR, not the average YTM of the bond. Please note, these are not identical quantities. I will talk more about it in later. It will be a digression if I talk about it at the moment. So, I will talk about them at a later point in time. Note that the portfolio IRR need not equal the average YTM of the bonds constituting the bond. This is a problem with the YTM. This is a drawback of the concept of YTM. I briefly touched upon this when I talked about the YTM, and when you talk about the YTM of a portfolio, it is not equal to, I repeat, it is not equal to the weighted average YTM of the bonds. The YTM of the portfolio needs to be calculated on the basis of the aggregate cash flows emanating from the portfolio at the respective times, and then using those cash flows when we equate the discounted value of those cash flows to the current market price, whatever is the discount rate, that will be the YTM of the portfolio. It need not be, I repeat, it need not be equal to the weighted average YTM of the constituents of the portfolio. Earning the IRR means the portfolio will grow to a sufficient future value to fund the liability. So, I will continue from here after the break. Thank you.